Hi everyone. So in our video today, we have a question that says that a furnace wall consists of 200 millimeter layer of refractory bricks. So we can sketch our furnace wall to be this, and it consists of 200 millimeter layer of refractory bricks. So this layer is our refractory bricks, and then it is 200 millimeters. So that's the thickness. And 6 millimeter layer of steel plate. So these are steel plates, 6 millimeters. Let's call this our steel plate. And 100 millimeter layer of insulation bricks. Now this is an insulation brick. It doesn't have an actual name. They are just calling it an insulation brick, which is 100 millimeter layer. So this is 200 and this is 6. The maximum temperature of the wall is 1150 degrees Celsius on the furnace side. So this side is 1150 degrees Celsius. And the minimum temperature is 40 degrees Celsius on the outermost side of the wall. An accurate energy balance over the furnace, so this is the whole furnace, shows that the heat loss from the wall is 400 watts per meter squared. So heat loss 400 watts per meter squared. So that means the heat loss is per area. It is known that there is a thin layer of air between the layers of refractory bricks and the steel pipe. So between this and this, because these are refractory bricks, and then the steel pipe, there is a thin layer of air between them, right? So it means that our steel here is now this part, and now this part is our air. We don't know the thickness of the air, right? So let's call it X. It is known that there is a thin layer of air between the layers of refractory bricks and steel plates. Thermal conductivities for the three layers are, so let's call this A, B, C, and D. So for the A, thermal conductivity of the refractory brick is 1.52 watt per meter degree Celsius. And then the of the layers, right? So the three layers are refractory bricks, our steel plate, and then our insulation. Right? So our KB, that will be for our steel plate, is 45 watt per meter degree Celsius. And then 0.138 to be that for the D, which is our insulation. So now let's ask ourselves, is air also an insulation? Yes, because air is an insulating material, right? So we can see that no, so this is for the steel KC. So KC, you can see that our KB for the air, thermal conductivity of the air will be the same as that for the insulation, which is 0.138 watt per meter degree Celsius. So now we know that from our previous lectures, we know that the heat transfer from this point to the end is the same as that from this point to this point, as well as from this point to this point, from this point to this point, and this point to this point. So we can see that since we have our overall temperature difference, we can see that our heat Q, we even deduced this in our previous video, change in T overall all over summation of the thermal resistance. So our Q, which is 400, is equal to change in T overall will be 1150 minus 40 all over. Then summation of our thermal resistances. So for this part, the refractory break, we are going to get 200. You convert it into meters, like all over the KE, but then it's per area. So we are just going to divide by the K, and the K was 1.52 plus We know that for conduction, the resistance is thickness all over Ke, right? But then the heat is per area already, so we need to include the area. And the next one is our air insulation. So the air insulation has a thickness. We don't know the thickness, so we are calling it X all over. The thermal conductivity was 0.138 plus that of the steel plate 6 millimeters, right? So 6 times 10 exponent minus 3 all over the thermal conductivity, that was 45, plus that for the insulation, so KD, which has a thickness of 100 millimeters, right? All over the KD is 0.138. So 400 is equal to, so when you evaluate this, you get 1110 all over. Now when we evaluate this plus this plus this, neglecting this portion, we are going to get 0.8575 plus then x over 0.138. So we can even evaluate this portion and see that 400 is equal to 110 all over 0.8575 plus, so 1 over 0.138, that will give us 7.246 x. Right? We are just making x a subject. So 0.8575 plus 7.246 x should be equal to 1110 over 400. So 0.8575 plus 7.246x should be equal to 1110 over 400, and that gives us 2.775. So we can transpose this to the right hand side, and then we'll be getting x is equal to 2.775 minus 0.8575 all over 7.246. So we get our x to be 2.775 minus 0.8575 all over 7.246, and that gives us 0.265 meters, right? Because you converted it here into meters, the moment you write x here, that means our x is supposed to be in meters, because when this isn't in meters, we can't even add them. So our x is in 0.265 meters or 265 millimeters. So now we come to our next question, which is what is the temperature of the outer surface of the steel plate? These are steel plates. So the outer surface is here. So let's call here T1, T2. Let's call here T3. So now we can just take this portion. Because we need T3, we are calling this portion T3. And then here is our 400, 40 degrees Celsius. And now this thickness is our insulation. So it has a thickness of 100 millimeters. Now we know that the heat transfer from this portion to this portion will still be the 400 watts per meter square. And then this is mean by conduction. So Q equals change in temperature will be T3 minus 40, because this will be at a higher temperature than this. All over our thickness is 100, so 100 times 10 is minus 3 all over K. So the K here, we need the K of the insulation, and that is 0.138, and this is equal to 400. So when we evaluate that, T3 minus 40 over, so 100 times 10 is minus 3 all over 0.138. So we get 0.7246 should be equal to 400. So our T3 minus 40 becomes 400 times 0.7246. And then we get T3 minus 40 is equal to 289.86. So now our T3 is equal to 289.86 plus 40. And then we get our T3 to be 329.86 degrees Celsius. Now our temperature here is 329.86 degrees Celsius.